Hey, good morning everyone. Welcome back again to Sri Chaitanya Educational Institutions channel, and in which we are we are having the bridge course for NEET 2026 preparation. As you all know that in this bridge course, we are not only strengthening our fundamentals, but we are also focusing on the crucial predictable problems. Those problems that have the probability to get repeated or to be coming in the NEET 2026 exam. And if the problems are crucial, then always there are multiple ways of solving them. There will be a conventional way or general way in which the other competitors of yours are going to handle that problem. But there will be always our way in which we are going to solve the big problems in by simple techniques. All right. In this journey so far, we have already discussed a lot of fundamentals related to the unit of kinematics, which will not be restricted only to that unit, but will keep coming in different chapters and topics. Similarly, in our last interaction yesterday, we talked about Newton's laws of motion and a very important fundamental topic of conservation of linear momentum. So today we are going to put a full stop on this conservation of linear momentum. I'll call today's interaction as conservation of linear momentum phase 2. All right, in which we will definitely revise whatever we have learned so far, but we will take this entire discussion up to a higher notch, up to a higher level, and then definitely we are going to entertain more number of models also. Okay, so few models we discussed yesterday. Let me give you a quick recap of everything, whatever we have learned. Then I'll take you towards some more models. So the discussion is conservation of linear momentum. The unit from which in which this topic is first we are expected to deal is Newton's laws of motion. So we started our discussion with Newton's second law. That we all know Newton's first law talks about the law, that is the law of inertia. Newton's third law is action reaction, but majorly we are talking here about the Newton's second law, which is also called as real law of motion. Real law of motion. Why we call this as real law of motion? Because in later discussions, I'll prove that in front of you that Newton's first law and Newton's third law can be proven as a consequence of Newton's second law. In simple terms, if you know what a Newton's second law is, then indirectly you can also comment about what is Newton's first law, and you can also comment about what is Newton's third law. Okay, but that is not something on which our today's discussion is focused on. Today's discussion is focused on conservation of momentum. It says if external force acting on the system is zero, then the system's linear momentum is conserved. Why that is so, sir? Because according to Newton's second law, external force acting on the system is responsible to change the linear momentum of the system with time. Remember, internal forces are not capable of changing the linear momentum, although internal forces can change the kinetic energy of the system. In the influence of, see, there is one mass, there is another mass. I have taken it also as an example. If you release these two masses, because of gravity, because of gravitation, they will be attracting each other. This phenomena is called gravitation. Okay, so the two masses were not initially moving. Now they both have started moving towards each other. So definitely they have gained some kinetic energy. So they have changed the kinetic energy in the influence of internal force. But initial their momentum was zero, and finally also they both are moving opposite, and their momenta will be exactly equivalent opposite. M1 V1, M2 V2 will nullify each other. So initial momentum was zero, final momentum is zero, which means under the influence of internal forces, system's momentum can't be changed. But kinetic energy of the system has been gained, which means internal forces are not capable of changing the momentum of the system, but they are capable of changing the kinetic energy of the system. Okay, internal forces can only change the kinetic energy or potential energy, but can't change the momentum. Momentum can be changed only by the application of unbalanced external forces. So this is Newton's second law. Suppose if F external is 0, if F external is 0, means there is no external force acting on the system, that means dP by dt will be 0. A quantity, a physical quantity whose differentiation is 0, that's the property of differentiation, that constant's differentiation is 0. So in the reverse order, we can say if dP by dt is 0, which indirectly says that P has to be a constant. Okay? There is also a difference between the terms constant and conserved. All this I already taught yesterday. I'm just giving you a quick recap. Right? So, if something is constant, means that is fixed throughout, which means its initial and final value has to be same. That means if something is constant, it is also necessary to be conserved. Conservation means initial value is equal to final value. But reverse is not true. Means if a physical quantity is conserved, that means initial value and final value are same. Then is it necessary that it will be uniform throughout? No. Initial and final are same, but it may vary in between. Alright. So if it is constant, then it is also conserved. But if it is conserved, initial and final are same, that doesn't mean that in between it will be fixed, and that doesn't mean it will be constant. So if something is constant, it is definitely conserved. But if something is conserved, it's not necessary that that's going to be constant. Clear? Now, according to Newton's second law, if F external is 0, then dP by dt is 0, means P is constant. But if P is constant, it also means it is conserved. That's why the name is principle of conservation of linear momentum. And if this principle says, whenever net external force acting on the system is 0, system's linear momentum is going to be constant or conserved. Because if it is constant, then definitely it is conserved. Clear? In this entire discussion, we have been talking about system. So choice of system is very important for all the conservation of linear momentum based models. With our journey ahead, you as a candidate will realize that what are the models in which principle of conservation of linear momentum is to be applied. Okay? So it's not going to be anything new in the exam. We'll be discussing all the relevant models. But in each and every model, we will be discussing choice of system is going to be very, very important. So what is the criteria, like what you should have in your mind, sir, so that you will choose the system? I will always choose a system in such a way that maximum available forces will become internal. The advantage of choosing the system in such a way that maximum available forces will become internal force is that then we can conserve the momentum. Okay? Because once again, I'll repeat, if forces are externally applied on the system, we can't apply the conservation of linear momentum, then what's the point of studying this much? Conservation of linear momentum is a tool, it's a technique which can be applied in a lot of problems in physics. So we want to apply conservation of linear momentum. If we want to use conservation of linear momentum as a tool or a technique, the criteria is that there should not be any, the condition is that there is no external force acting on the system. So choice of system must be made in such a way that all the available forces will become internal, and hence the conservation of momentum can be applied. For example, that is in front of you. If there are two bodies A and B, and I have written choice of system is very important. If there are two bodies A and B under, say, mutual gravitational interaction, they are attracting each other. Two masses will always attract each other. Gravity. So gravitation. So here I will say that this force on A due to B, this force is acting on A externally. This force is acting on A externally. So with time, it will be changing the momentum of A. It will be changing the linear momentum of A. Similarly, this force acting on B due to A, it is acting on B externally from outside. So if it is acting on B, it will be changing the linear momentum of B. But if you consider A and B total as a system, this white colored part, if you consider A and B total as a system, system is A and B both, in that case, the two available forces will become internal forces. The forces existing between the inner parts of the system commonly can be called as the internal forces. So the moment you have deliberately chosen a bigger system, the moment you have deliberately made those two forces an internal force, the advantage is that you can apply the conservation of linear momentum. So now external force acting on the system is zero, as these two will be equal and opposite internal forces will become internal forces, and these will be equal and opposite by Newton's third law. Anyways, if they become internal forces, action reaction, then external force is zero, system's momentum can be constant or conserved. Okay, which means final momentum must be equal to initial momentum. And if the system is starting from rest, means initial momentum of both is zero, then finally m1v1 plus m2v2 vector will be equal to zero, which means if you consider the sign forward and backward, you will realize m1v1 vector will be minus of m2v2 vector. This minus is only mentioning that they must gain the momenta. Final momenta must be gained in equal and opposite fashion. Minus sign is showing opposite. In equal and opposite fashion, so that final momentum, just like initial momentum, will become zero. That's what we have learned fundamentally. Newton's second law. Newton's second law resulting into conservation of linear momentum. When we say momentum will be constant, constant always means it is conserved, but vice versa is not true. In this example, the choice of system is something we need to emphasize on. On A, if the force is acting externally, then that will be capable of changing the momentum of A. On B, if a force is acting externally, then that will be capable of changing the momentum of B. If you consider both as a system, then definitely you will say that the forces available will become internal force that have the capacity, that have the capability to change the kinetic energy with time, but they don't have the capability to change the linear momentum with time. These are the fundamentals. If you haven't taken the screenshot earlier, if you are listening to it for the first time, then I would suggest you to take a screenshot here. All the notes will be attached in the description of the video, but because, in order to revise in between, definitely you can take the screenshot. In short intervals these days, you can keep revising the things, and I'm hopeful and I'm sure that you would be following the rule of revision. Okay, rule of revision says whatever things you have learned from morning to evening in these online or offline sessions, before you sleep tonight, you must be revising the things, because when you revise the things before sleeping, throughout your sleep, those things get stored in your stronger memory. Okay, so there will be no problems like, sir, we keep forgetting the formula, we forgot the approach, we keep moving ahead, we enjoy learning physics, but whatever we have learned 2 months back, we forgot completely. These problems will be eliminated. Okay, follow the rule of revision. Now, going towards the next part, that is, if sometimes the overall external force acting on the system is not zero, so overall system's momentum cannot be conserved, but in a particular direction, in a specific direction, you have external force zero. So conservation of momentum tool or technique can only be applied in that specific or particular direction in which the external force acting is zero, which means here, if F external on the system is non-zero in such a way that along the y-axis it is non-zero, say because of gravity, in most of the cases gravity will be acting in the y direction, but suppose there is external force in the x direction is zero. In that case, you can't conserve the overall momentum of the system, and you can't conserve the momentum of the system in y direction, because there is an external force which is capable of changing the momentum. But since there is no external force acting on the system in a particular direction called x-axis, suppose, then you can conserve the momentum of the system along the x-axis. Means final momentum along the x-axis must be equal to initial momentum along the x-axis. Okay. During the discussion of x-axis, while taking the problems in class, I'll stick to the convention that I'll write the forward vectors as positive, backward vectors as negative. Similarly, during the y-axis discussion, I'll be taking upward vectors as positive and downward vectors as negative. All right? Right. Let's move ahead. Now, the basic models related to conservation of momentum are based on the fact that the momentum or velocities especially will be given with respect to ground, and the asked momentum or velocity will also be with respect to ground. Given velocities are with respect to ground, asked velocity is also with respect to ground. So principle of conservation of momentum will also be applied with respect to ground. But the complex models which you must be expecting in the NEET exam, it's a national level exam in fact. No one is going to ask you directly the very simple model. It's not going to come. But we will compare both of them, and then we have already compared and we developed our understanding what to do in this one. So the complex model or the relative motion based model means what is the core difference between the two? In this case, the velocities are given with respect to ground and asked velocities are also with respect to ground. In this case, the given velocities and asked velocity, one of them will not be with respect to ground. One of them will be the relative velocity. So this model is conservation of momentum in which it is based on relative motion. This model is conservation of momentum in which every velocity is also with respect to ground and conservation of momentum must also be applied with respect to ground. And you can see both the situations are same, gun and bullet situation. Okay. So definitely the model which you are expecting to be coming in the NEET exam is going to have a big analysis and solution, to which I have also given a shortcut here onwards. So first of all, we will try to understand, we will develop our understanding of the difference between the two models. Then we will see that we know that this type of model will be coming in the NEET exam and we don't want to do this much. Then how we can skip, how we can directly jump to the final step, the shortcut method. I'll tell you that. So before that, let us compare it once again. So you have a gun, there is a bullet inside it. Initially the system is at rest. Now you fire it. Okay, fire the bullet. So the bullet's velocity V0 is given with respect to ground. If they don't mention anything, then bullet's velocity is with respect to ground. Okay. And gun will experience a recoil. Definitely action reaction, Newton's third law. Or you can say by conservation of momentum, if one body is gaining the momentum in the forward direction, another one must be gaining the momentum in the reverse direction. Then only they will nullify each other. Why nullification is important, sir? Does the principle of conservation of momentum says that the momentum must always be zero? No. Momentum will be zero only if initial momentum is zero. Here, initial momentum is zero and there is no external force acting on the system. So no one is there to change the momentum of the system. So definitely the final momentum must be zero. System's final momentum must be zero. Now because of gun, there will be a force applied on the bullet. So bullet's momentum has been changed. For every action, there is an equal and opposite reaction. So bullet will also push the gun. So gun's momentum has also been changed. Because of the internal forces, which are basically the external forces on the individual parts. So individual parts will change their momenta. But the system's linear momentum is not going to be changed. So that's what it happened here. That if you consider system as bullet plus gun, the external force acting on the system is zero. Because you have considered both of them as the part of your system. And if there is no external force acting on the system's momentum can be conserved. That's what you have written. Mass of gun, velocity of gun, mass of bullet, velocity of bullet is zero. Here we have applied this. We have applied conservation of linear momentum. We have applied conservation of linear momentum with respect to ground. With respect to ground means all the velocities were given with respect to ground and the asked velocity, recoil velocity is also required with respect to ground. So you have just written it this way. Mass of gun is capital M. Gun's recoil velocity is towards left. So I have taken it as minus VR plus mass of bullet is M0. The bullet's velocity is V0, that is equal to 0. This velocity V0 is with respect to ground. So the given velocity is with respect to ground. The asked velocity VR, recoil velocity is also with respect to ground, and hence the principle of conservation of linear momentum is also applied with respect to ground. That's the scenario. Okay. Understood? If in this case you say bullet's kinetic energy is given, if bullet's kinetic energy is given, then the final answer can be in this way. Recoil velocity, this M0 V0 is nothing but the momentum of the bullet. Momentum of the bullet. So that will be the momentum of the bullet by mass of gun, capital M, where kinetic energy is equal to half mv square is equal to p square by 2m. I hope everyone knows. In that case, P can be written as kinetic energy is P square by 2m. So that can be written as under root of twice of mass m naught into kinetic energy of bullet, okay, by capital M. Means we are interested in writing the conservation of momentum. The results can be m naught v naught by m, which I told you no one is going to directly ask, right? It's a very simple approach. For NEET national level exam, definitely you have to, you have to expect something, something involving some sort of complexity, or I won't say complexity, but a higher level of knowledge. So here, you need to understand that if m naught v naught is nothing but the momentum of the bullet, then there is another relation in your syllabus of kinetic energy. Kinetic energy is equal to P square by 2m. That means P can be written as under root of 2m kinetic energy. So mass of bullet, kinetic energy of bullet, by in the denominator the mass of gun was as it is. Okay. So see, the first phase of discussion we have already discussed it yesterday. I'm re-emphasizing on the things. So I hope this discussion entirely is clear to you, in which once again the given velocities with respect to ground, the asked velocities with respect to ground, and hence you have applied the conservation of linear momentum with respect to ground. Now the story 2. Same situation, gun, bullet inside it, the bullet is firing, the gun has fired the bullet here, but the bullet's velocity is the muzzle velocity given. You would have heard about this term, or else you will, keep looking, you'll be hearing about this term for sure. So, muzzle velocity is basically the velocity of the bullet with respect to gun. Muzzle velocity is velocity of bullet with respect to gun. So, what is given to us here? Relative velocity. And what they have asked you is the recoil velocity, which is definitely with respect to ground. Because, you are the person who is standing on the ground, then firing the bullet, you will experience a recoil. So that is with respect to ground. Okay. So they are asking you ground's velocity, with respect to ground velocity, but they are giving you the relative velocity. So the things will be not as direct as they were here. So now what to do? We will still apply the conservation of linear momentum with respect to ground. So you will again write the same situation. V mass recoil velocity with respect to ground, bullet's mass, bullet velocity with respect to ground vectorially can be given by vector addition of bullet's velocity with respect to gun plus gun's velocity with respect to ground, which is also called as recoil velocity. Once again, bullet's velocity with respect to ground, which we want to write, can be written as bullet's velocity with respect to gun, which can also be called as muzzle velocity. Muzzle velocity. Bullet's velocity with respect to gun is muzzle velocity. Gun's velocity with respect to ground is recoil velocity. That is equal to 0. Once you put everything along with plus minus sign, forward positive, backward negative, you got the final answer as this. That recoil velocity is mass of bullet. Once again, recoil velocity of gun is mass of bullet into relative velocity. Muzzle velocity is nothing but relative velocity. Muzzle velocity V naught is nothing but relative velocity. Try to understand the pattern. Try to understand the pattern. Recoil velocity for gun is equal to mass of bullet. Always take opposite mass. Mass of bullet into relative velocity over total mass of the system. Mass, always take opposite mass. If you are writing the recoil velocity of gun, then mass should be taken for the bullet into relative velocity by total mass of the system. All right. So this is always take opposite mass. Always take opposite mass. I hope the comparison of the two cases is clear to you. I would want you to take a screenshot of this. And then I'll tell you, I'll re-emphasize on this shortcut. Are you understanding the shortcut? If you are writing the velocity of the bullet, then it should be mass of gun. If you are writing the velocity of the gun, then it should be mass of bullet. Always take the opposite mass into relative velocity by total mass of the system. See the same pattern over there. Okay, take the screenshot, then we will talk about many times about the same pattern, many different models. I hope that's clear. All right. Let's go for the next one. Yeah. Special focus on the two particle system. Always take opposite mass. Very important for NEET. I told you this yesterday. And again, I have taken the same illustration to tell you that you can skip any analysis and derivation and you can directly write the final results. If initially the system is at rest, there is no external force acting on the system, momentum of the system is conserved, and the relative velocity is given to you. Okay. When all the velocities required and given are with respect to ground, then obviously you will go for the direct conservation of momentum. But if the relative velocity is involved in the picture, then definitely you can, follow the technique which I am telling you. Always take the opposite mass into relative velocity by total mass of the system, along with plus minus sign in the velocity or any vector will only contribute in the direction. You have heard about all these things from my side many times. Now, if you fire this, recoil velocity of gun will be experienced, in the left side. So velocity of gun with respect to ground or recoil velocity will be minus. Minus means left here. Always take the opposite mass. So if you're writing the velocity of the gun, you will be writing the mass of the bullet, m0, into relative velocity v0 by total mass of the system, m0 plus m. Similarly, if they ask, tell me the velocity of bullet with respect to ground. This was the velocity of bullet with respect to gun. If they ask the velocity of bullet with respect to ground, then it is positive because it is right. Always take the opposite mass. If you're writing the velocity of the bullet, the mass must be taken of the gun. Mass of gun into relative velocity, V0, muzzle velocity, by total mass of the system, M0 plus capital M. Easy, directly writing the final result. Another example, another illustration, illustration 2. There is a boat over the surface of water. What is the significance of taking a boat problem over here? Because the external friction offered by the water layers on the surface of the boat, is negligible. So there is no considerable external force, it is negligible, and hence system's linear momentum can be nearly conserved. But if there is a man who has to walk over the boat, then for me to walk over a surface, there must be a friction. So the friction acting on the shoe of the man is the external force acting on the man. So man's momentum is changing. Its reaction is this. For every action, there is an equal and opposite reaction. The reaction friction acting on the boat is an external force on the boat, which will change the momentum of the boat. So man is experiencing friction, man's momentum is changing with time. Boat is experiencing friction, boat's momentum is changing with time in the left side, right? But if you consider man plus boat as a system together, then the same friction will become an internal force. And if the same friction will become an internal force, then definitely system's momentum cannot be changed. There is no one in the picture who can change the system's linear momentum. That's what we wanted. We always wanted to conserve the linear momentum of the system. We wanted to use it as a tool or technique. But when the man is walking over the boat, then the velocity with which the man is walking, that must be the velocity with respect to boat. Because the man is walking over the boat, so its velocity is obviously the relative velocity. If the man is walking over the boat, with whatever velocity it is walking on the board, relative to the board. That's why I'm emphasizing again and again that this velocity is not the velocity with respect to ground. This has to be the velocity with respect to boat. Alright, so what is the situation now? Relative velocity is given, two particle system. Examiner might ask you, tell me the recoil velocity of the boat or a plank, or tell me the actual velocity of the man with respect to ground. So if you want to write actual velocity of boat with respect to ground, since the boat will be moving towards left, it should be minus. Always take opposite mass. If you are writing the velocity of the boat, then the mass should be the mass of the man. Minus because of left, always take the opposite mass into relative velocity by total mass of the system. Okay. Similarly, if you are writing the actual velocity of man with respect to ground, which means you will be getting plus, because it was moving right, always take the opposite mass. So it is mass of boat. If you are writing the velocity of man, then that should be the mass of boat into relative velocity by total mass of the system. Is that clear? All right. There would have been another way of getting this. Alternatively, you could have written it like this, that I need some more space. Okay. Yeah, I'm writing it here. See, or else how could you get that? If you're writing velocity of man over the ground, then you will be writing velocity of man over the boat plus velocity of boat over the ground. I hope you agree with it. Man over the boat plus boat over the ground will give you man over the ground. First on the second plus second on third will give you first on third. Let us verify. So velocity of man over boat, it is moving in the forward direction with respect to boat, it is plus u. Okay, plus velocity of boat with respect to ground, you have got it as minus of m naught u by m naught plus m. See, I'm substituting all the vectors with plus minus sign here. So that will be equal to, if you take the LCM, that's m naught u plus minus will be minus m naught u. Okay, here it is m naught u plus capital MU plus minus minus m naught u by m naught plus capital M. As you can see here that this m naught u and minus m naught u has been cancelled. So what you got is, that means velocity of boat with respect to ground, velocity of man with respect to ground, which you were finding here, that velocity of man with respect to ground is again positive of capital M into u by m naught plus capital M. Did you get the idea? So even if you do by vector resultant, vector addition, relative velocity formula, or you do it by, the shortcut which I have told you, you need to understand that you got here the same result. You got here the same result. Now, is it necessary to have a two particle system only, sir? Can't we have more than two particles in our system? 3 particle, 4 particle? We can have. But first of all, we are trying to understand the simple and more predictable models. Majority of physics problems will be two particle, two charges, two masses, satellite and planet, two things, electron and nucleus, two things. Majority of systems are going to be two particle system, binary stars, two particle system. All right, understood, no? So that is the entire discussion. Always take the opposite mass. Now we will keep taking more and more models. This was bullet plus gun model. This is man plus boat model. I hope you have understood. Now we can take more models. If you want, you can quickly take a screenshot. All right. Yes. Now, seashore problem. In this seashore problem, there is a seashore, obviously a part on ground. So you have to apply the conservation of momentum with respect to ground. Now at a distance, a specific distance, there is a boat, and over the boat, there can be a man or a pet or a dog, anything here, right? So what is happening? The situation is that initially let me show you the actual problem once again. There is this man standing on one corner of the boat, and the boat is over the surface of water, right? Obviously offering negligible external friction. Internal friction will be there, which may change the energy, but will not change the momentum. So conservation of momentum can be applied. This is one of the important models. Now here, examiner is asking you, when this man will reach the other end of the boat, what is its final separation from the shore? So generally we think that initial separation is x naught plus L. When this man will reach the other end, its separation will be x naught. General thought, but it's a wrong thought. The reason is, when the man starts moving on that side, the boat will start shifting on this side. So its final separation will be definitely less than x naught plus L, but it will not be x naught. It will be somewhat more than x naught. See, when the man reaches the other end, the boat also shifts somewhat like this. Okay, the boat also shifts somewhat like this. So its final separation will be x naught plus some distance, plus this distance here. This distance is also from here to here, there is some shift. Getting it? No, there is some shift. So how to write it, sir? How to write it? The same pattern which you have applied for the velocity, or that always take the opposite mass, the same pattern we will directly orally apply and write the answer in one step for the displacements. Okay. So final separation of man from the shore, position vector, final separation position, will be equal to its initial position plus some displacement you have traveled. My final position is where I was initially and how much I have been displaced. Okay. So initial plus the displacement. So initial will be x naught, and it is in forward direction. So, I have indirectly taken it as positive only. See, forward direction, positive x naught. plus displacement you are covering in minus sense. So there is a minus because you are moving left, but you have to write the displacement of man with respect to ground. But the issue in this problem is that the man is moving over the boat, means relative displacement is L, but you are interested in writing with respect to ground. So easy. It is minus because of left. Since you are writing the displacement of the man, always take the opposite mass. So you should be taking the mass of the boat into relative displacement L by total mass of the system m0 plus m. If you are writing the displacement of man, you should be taking the mass of the boat into relative displacement by total mass of the system. Negative sign because it was moving left. If you simplify, you will get the final answer here. All right. Understood now? Now, look at this example. There is a seashore data, numerical database problem, exact the same situation, but the difference is that here the man was walking near to the shore. There the man is walking, the dog is running on the boat away from the shore. So 45 meters is the initial displacement in the forward direction. The dog is also moving in the forward direction. 5 meters is the length of the boat. So final separation will be initial separation plus displacement. Last time the displacement was negatively substituted because of the left. This time the displacement of the dog will be positively substituted. Positive here, positive, right, rightwards. All right. So 45 meters is initial plus, since you are writing the displacement of the dog, you should be taking the mass of the boat. Always take the opposite mass, 90 kgs into the relative displacement 5 meter by total mass of the system, 90 plus 10. Substitute everything, you got the final answer. Okay. So generally it seems that you have traveled 45, then you have traveled 5, so the total should be 50. But when you are moving ahead, the boat will be shifted a bit back. So the final answer must be less than 50. And see, what we got is 49.5. Definitely it is less than 50. Any doubts, anyone, anywhere till now? Any doubts? You can post it over the live chat section. I would love to answer your doubts. Yeah, but I think whatever we have discussed yesterday and the recap of that, I have taking a lot of time today. That is clear for you. Definitely we are expecting one direct problem from all this in NEET 2026. So, okay, thank you. Right, any doubts? Okay, chalo. Let's move on to the next one. Block over the wedge, another model, block over the wedge. Again, that also I have taken yesterday only, again re-emphasizing on that. But here the twist in this model is that if you release a block over the wedge can only move in horizontal direction, but the block will be moving forward and also downwards. Means the wedge motion is along a straight line. Wedge or inclined plane, its motion is only motion along a straight line. But the block's motion is the motion in a plane. Okay. Now, in the y-axis, you can't conserve the momentum because gravity is always acting externally. So because of gravity acting in y direction, you can't conserve the momentum in the y direction. But see the question is determine the horizontal displacement of the block and wedge when block reaches the bottom. Means the examiner is also asking you horizontal things because you are technically allowed to apply the conservation of momentum in the horizontal direction. You're not allowed to apply the conservation of momentum in the vertical direction due to gravity. All right. So this distance can be base length x0, this distance can be height, this distance, the length of the inclined or the wedge can be given by Pythagoras. Everything is smooth. There is no external friction acting on the system. System's momentum can be conserved. This mass is not fixed. Okay. Both are movable. So if they are asking you anyone's displacement, as I am mentioning again and again, you can directly write the final result. Let us write the final result, keeping for two particle system, keeping this in mind that you have to take always the opposite mass. Okay. So if you are writing displacement of block on the ground horizontally, so if you are writing the displacement of the block, it is forward in the horizontal, then whose mass is to be taken? Wedge mass is to be taken. So wedge mass is capital M. Into the relative displacement. Relative displacement in horizontal direction is x0. We are writing it as relative displacement in horizontal direction. Okay. x0 is the relative displacement in the, like the displacement covered by the block over the wedge in horizontal direction. That is base only. Relative displacement in horizontal direction. Okay, ji. That is the situation. And here conservation of linear momentum can be applied only in horizontal or x-axis, not in y-axis due to gravity. Now, if you're writing the displacement of the block, you need to take the wedge mass and it is in the forward direction. That's why plus relative displacement x naught by total mass of the system. Similarly, if you're writing the displacement of the wedge, try to feel it. By the time block will be moving down and forward, the wedge will keep on moving leftward. Backward means negative. If you're writing the displacement of the wedge, you need to take the mass of the block, m naught, opposite mass, into relative horizontal displacement by total mass of the system. Clear? Let's take a numerical model here. It's not necessary every time that they will give you the base length. They might give you the length of the inclined plane or the length of the wedge, this inclined length. Then you can apply a basic trigonometry, man. The base will be L cos phi. If phi is the angle of inclination, the base will be L cos phi and the height will be L sin phi. Y naught coordinate or height will be L sin phi. So if you are writing, first of all, let's talk about the wedge. Wedge is not at all moving in y direction. So wedge displacement in y direction is 0. Wedge is only moving in horizontal direction. Wedge displacement in horizontal direction is towards left minus, always take the opposite mass, block's mass m naught into relative horizontal displacement. Relative horizontal displacement is L cos phi by total mass of the system. But if you write the block's displacement, then block is moving in x-axis as well as in y-axis. Y-axis, it is only moving down to the ground. So how much it is traveling? Minus L sin phi. Minus because of down and L sin phi. Okay. And because if you are trying to write in the x direction, then you will conserve the momentum and you will apply my shortcut. My shortcut is always take the opposite mass. So if you are writing the displacement of the block, since it is moving in the forward direction, it is positive. Always take the opposite mass. If you are writing for the block, so mass should be the mass of the wedge into horizontal relative displacement L cos phi by total mass of the system m naught plus m. I think it is clear. Everything is clear for you. If you want, you can take the screenshot. Yes, strike out, dear. I have read that and thank you so much for the appreciation. And I'll keep working. In fact, we as complete team will keep working hard for all of the aspirants who are preparing for NEET 2026 also. So you also, the way you are appreciating, I would suggest that you also share these, knowledgeable sessions, these video links to other friends who can still start preparation from their home if they are still waiting for the NEET result. And I know a lot of our friends are still waiting for the NEET ranks and then they will decide what to do. But these days, even if you are having a safe score, there is no harm in revisiting these concepts, because in the first year of the we have produced a lot of good score this time also for all those students. The first year syllabus is also going to be related to all this stuff, so you can still take the benefit of that. But yeah, most importantly, you should try circulating this to all our friends who are preparing, and they are very hardworking and sincerely preparing from home for the NEET 2026. So we will try to target each and every relevant model over here. Okay. Now, let me take you towards the next, that is man plus balloon problem. Man plus balloon problem. So in this situation, there is a balloon over here. Okay. This is the balloon. And this is very light rope. This is very light rope. Light rope. Inextensible it is. Inextensible. Like an ideal string, massless and inextensible. Its mass is capital M over here. Its mass is capital M. And there is a man of mass m0 over here. This is, say, the h0 height from the ground. So there is a h0 initial height from the ground, initial height of the man. This is the length of string, capital L. This is the length of string from here to here, capital L it is. Okay, length of string is L, length of rope is L. And initially, the system man plus balloon is floating in the air. Floating in the air. That is the situation. Initially, the system is floating in the air. How is it possible, sir? Floating means we are talking about equilibrium. Floating condition is basically an equilibrium condition. That is, there are two forces acting on it. W is equal to mg and the buoyant force. So W, which is equal to capital M plus m naught into g. Okay, total weight will be equal to the total buoyant force. Total buoyant force and external force, net external force acting on the system is 0. Okay, net external force acting on the system is 0. What is the formula of buoyant force? How do we write that? How it is capable of balancing? All these things are useless for now. We will talk about it at right time in fluids. But right now we are only interested in the fact that if it is floating, which means it is in equilibrium, net external force acting on the system is 0, which means conservation of momentum can be applied. System's momentum will be conserved. System is man plus balloon. System's momentum will be conserved. Okay. Now the type, so this is the analysis of the system. Like, what do we understand about it? What is the question? Now let's talk about the question. Question is, determine the final height. Determine the final heights of balloon and man. Determine the final heights of balloon and man when man climbs to the other end. When man climbs to the other end of the rope. To the other end of the rope. I hope you have understood this. Basically, if the man has to climb over the rope, even for hanging, even if the man wants to just, hang, there has to be a friction. The rope cannot be smooth, because if the rope will be smooth, the man will slip down under the action of gravity. Right? So if the man wants to even stay there, or more importantly here, if the man wants to climb over the rope, there has to be a friction between the hands and the rope. But that friction will become an internal force here. And if that friction will become an internal force, again there is no external force, again the system's momentum can be conserved. Alright. So now you have to write the final heights of both of them. So see, one by one I will write both. First of all, I am writing the final height, or let me write the y coordinate from ground. Okay, height and depth are always from the ground. So y coordinate of man with respect to ground finally. So you will say that will be y coordinate of man with respect to ground initially plus displacement covered by the man with respect to ground. Again the same logic, that final is always initial plus whatever change you have considered. So whatever change is brought in the system or situation of the system, I would say. So basically initially I was there, you displaced me somewhere, I got my final position. So final height will be initial plus the displacement traveled. So initial here, if you are writing the man's displacement with respect to ground initially, so man's displacement with respect to ground, or a man's position with respect to ground initially is basically plus h naught, because it was upwards, plus h naught. From the ground it is vertically up, h naught. Now it is further climbing up. If it is further climbing up, then it is positive, and always take the opposite mass, because when the man climbs, man actually covers a displacement of L over the rope, which means relative to the rope or relative to the balloon. Man is covering a displacement L in order to climb to the other end, but that displacement is covered over the rope with respect to the rope or with respect to balloon. That is basically relative one. So if you are writing the displacement of a man, always take the opposite mass. The opposite mass is the mass of the balloon, capital M, into relative displacement L by total mass of the system, m naught plus capital M here. Okay. Now I will say that everything is positive here. So that is h naught plus ml by m naught plus m. Very simple. Very simple. But what about the other one? What about the displacement of balloon with respect to ground? Finally, so I will say, which means it is nothing but the height. So that will be initial one, balloon with respect to ground, initial plus the displacement of the balloon with respect to ground in y direction, right? Now initially the balloon's height is h naught plus L. Initially the balloon's height is h naught plus L. Okay, h naught plus L plus, now if the man is climbing up, naturally the balloon will be going down. One part of the system is moving up, so the other part must be moving down. Conservation of momentum, they must nullify. Okay, because initial momentum is 0. Here I can write further, this implies final momentum of the system must be equal to initial momentum of the system, but initial momentum of the system is a null vector. System was not moving, no part of the system was moving. So finally also they must nullify each other. One is moving up, so the other one must be moving down. If it is moving down, it has to be a minus. Always take the opposite mass. If you are writing the displacement of the balloon, it should be the mass of the man, m naught, into relative displacement L by total mass of the system, m naught plus. I hope that's clear to you. Is it clear now? Okay, so if you want to take the LCM, it is m naught L will be cancelled, and I think you will get the other expression also. So that's how you can write both the things, I would say. That's how you can write, both the displacements. Finally, where is the man, and when final height of, if the man reaches the other end and the balloon is also down, then definitely both are meeting. When the man is moving up and the balloon is moving down, finally both are meeting. So their final heights must be same. So even if you solve this and if you solve this here, I should write final heights. I'm writing it here. This and this result, final heights, because they are meeting, no, finally. So final heights must be same as they meet. Okay. So when the man reaches the other end of the rope, the man basically meets the balloon. So finally they must be at the same height. So solve this, you must get the same result. In fact, I can do it for you. See, this is h naught plus, if you take the LCM, it is m naught L minus m naught L knocked out. So it is capital ML by m naught plus capital M. I hope the logic is clear to you. So there are many minor logics which will be visible. Like, generally students, what they do, they solve the question, get the answer, see the answer key and move on. They don't analyze the solved problems. But here we are going to train you, we are going to tune you in such a way that you fight with the problem, go through the approach, get the result, but don't be happy and move on. No. Once you get the result, you try to analyze that how, if the same problem comes in the final exam, can we do it in one step? Or what is the significance of getting such a pattern of the final answer? So this approach of learning is called paternalistic approach, pattern-based approach of learning, which is a integral part, which is a key part in our training for the NEET exams. All right, we get the final result, we are happy, okay, but we also try to understand that in such type of models, why every time the same pattern is coming? Can we understand the pattern? Do we understand the restriction of the pattern? And can we have some more models in which every time we can write the final answer in 1-2 steps? See, every time, whatever they ask. In the NEET exam, they won't be asking you everything. I am discussing everything. They will be asking any one part of it. I hope that's clear. Okay, take the screenshot. Mr. Theories, all doubts, sir, don't know, sir. It's okay. You might have joined just now. This is the phase 2 of conservation of momentum. It's okay. You relax. In your free time today, you go through the last discussion. Last discussion was like yesterday I have taken. Go for yesterday's live session in which I have started this discussion from the fundamental of conservation of momentum. Today also, if you would have been there at the right time, students, don't delay. When there is a live class at 10, be there ready with pen and paper at 10. Okay, because I every time start from the basics. Now the implementation, the utilization of concept is being there. We will implement the concept every time. We will start from the basic. First half an hour, 40 minutes, you have to understand, build up your fundamentals. So if you join at the time of problem solving, you might not be able to relate. Strengthen your basics first, strengthen your fundamentals first. That is the key agenda of this bridge course, no? Be at right time from tomorrow. And all the students who have missed anything previously, make sure that, you binge watch these sessions. Try to take some good time, 5-6 hours, and, adjust the speed of the recorded lecture of these lectures according to your pace of learning, and just go through number of them. Okay, slowly, in 2, 3, 4 days, you will be able to make up with all the things which you have missed. Then the journey will be smooth. Take the screenshot. We are going ahead. All right. So now, 2 men on the boat. Single man on the boat we have understood. Now we are writing 2 men on the boat. So there is a boat. Okay, there is a boat. Mass capital M, and the boat, the significance of this situation is that there is no external considerable friction. You can ignore the external force. So you will say system is initially at rest, which means initial momentum of the system is 0. So, and since there is no external force acting on that, the system's final momentum must also be nullified, 0. There is a man of mass m1, there is another man of mass m2. Okay, m1 and m2. And m1 starts moving with u1 velocity and m2 starts moving with u2 velocity. These u1 and u2 are with respect to, these velocities are with respect to boat, because both men will be running or walking over the boat. So their velocities are also relative to the boat. Question is very simple. Determine the recoil velocity. Determine the recoil velocity of boat. Determine the recoil velocity of boat, and you have to understand this, that this recoil velocity is with respect to ground. With respect to ground. All right. So one way of doing that is I can do a big way and apply the conservation of linear momentum, writing every velocity with respect to ground. Can be done. Can be done. So way 1 of writing it is, let me write that for you. Way 1 of writing it is that final momentum of the system, mass of boat into velocity of boat with respect to ground vector, plus mass m1 into velocity of 1 with respect to ground vector, plus mass m2 into velocity of 2 with respect to ground vector. That must be equal to initial momentum of the system, which is 0. Final momentum of the system must be equal to initial momentum of the system. Suppose the recoil velocity is this side. Although we don't know, if m1 runs with a greater momentum, then recoil will be observed opposite to it. But if m2 runs with a greater momentum, then recoil will be observed opposite to it. We don't know where it is, because all of them are symbols. None is the numerical value. So we don't know. So we have to assume, we have to suppose that, suppose the recoil velocity is towards the left. Okay. So I'll write it as, this is the mass of boat capital M. Recoil velocity of boat with respect to ground, it is this only. Okay. Recoil. Plus m1, velocity of 1 over the ground can be written as velocity of 1 over the boat, plus velocity of boat over the ground, which can also be written as recoil. Recoil. All right. Plus m2, velocity of 2 with respect to ground can be written as velocity of 2 with respect to boat, plus velocity of boat with respect to ground, which is again recoil, v recoil, and that is equal to 0. That is equal to 0. So I have just applied the relative velocity statement the velocity of one with respect to, see, we are basically applying conservation of momentum with respect to ground, because recoil velocity was asked with respect to ground, although the given velocities were with respect to boat. So what to do? So we will write it this way, and then I will substitute everything along with the plus minus sign. So the mass of the boat is capital M. The recoil velocity vector as per our assumption is minus VR, because convention is all left things I will be taking it as negative, plus M1 recoil velocity, velocity of 1 over the boat. Velocity of 1 over the boat, diagrammatically it is forward, so I'll be writing it as plus U1, and again the recoil velocity I am adding, so it is minus VR plus M2. The velocity of 2 with respect to boat, diagrammatically it is towards the left, so it is minus U2 minus VR, that is equal to 0. All right, you can solve this, you can get the value of VR. So that is equal to minus MVR plus M1 U1 minus M1 VR minus M2 U2 minus M2 VR, that is equal to 0. From here, this term and this term you can take on that side. The other side. So all these terms will become positive, and then you can isolate VR, get it in the denominator, get the remaining coefficient in the denominator. VR is given as M1 U1 minus M2 U2 by M1 plus capital M plus M2. This is the recoil velocity. Here. All right, and that recoil velocity is towards left. Magnitude wise, it is this much. Direction wise, it is going to be towards left. So that is your final answer. All right, M1 U1 minus M2 U2 by M1 plus capital M plus M2. That is your final answer by this big approach. Way 2 of doing that could have been way 2, our way of doing it. Sir, we don't like this much of relative velocity. We don't want to talk about relative. We don't want to talk about apply conservation of momentum with respect to ground, with respect to boat, with respect to frame of reference. We don't like that much. We like pure physics. We like to feel it. Then what to do? So I will say I have given you the feeling and rule of always taking the opposite mass only for a 2-particle system. But this time it is 3-particle system. M1, boat, M2, there are 3 particles. No issues. We will apply superposition. We will say net effect is summation of individual effects. I'll assume that this given situation is superposition of 2 things. Imagine that this M2 is not moving, only M1 is moving with U1. Only M1 is moving with U1 and M2 is not moving, that is stick. So this time this will be recoil velocity 1, VR1. Okay. Now imagine that M1 is not moving, only M2 is moving with U2. So definitely there will be this recoil velocity 2, VR2. Correct? VR2. So can I say if both are moving, then you move one at a time and write down the final answer. You move one at a time and try to write down the final answer here. See, I'll write it for you. So I will say here, VR vector net, VR recoil velocity net can be written as VR1 vector plus VR2 vector. Now, naturally, one is negative, one is positive. So, one is negative, that one is negative minus, and how to write it? Plus, another one is positive, and how to write it? So, I will say, if you are writing that VR1, then that is the recoil velocity of M2 plus boat. So, always take the opposite mass. That opposite mass is M1 into relative velocity is U1 by total mass of the system M1 plus you have assumed that M and M2 are together. Then only that will be a 2-particle system. Na? This will be 1 particle and this will be another particle. 2-particle system. You are not interested in dealing with 3-particle, doing this much, writing that, because I am your teacher. I can write it and in my presence you will like and understand everything. The challenge arises when I'm not available with you. So in that case, would you like to write down the entire frame of reference, relative velocity, this, that, or understanding this is easy? Understanding this will be easy because what you are doing is you are converting your 3-particle system into 2 at a time. So one time M1 is moving and M2 and M are sticking together, behaving common body. Similarly, another situation, M2 is moving and M1 and both are sticking together and behaving a common body, behaving like a common body. So VR2 vector, since it is attained in the forward direction, I'll be writing it as positive, and it is always take the opposite mass, means M2 into U2 by M1 plus M2. Since you are assuming that overall recoil is in the left direction, let us take the minus sign common, So what you have here is directly M1 U1. It was positive, but you have taken the minus sign common, it is minus M2 U2 by, and the total mass here is capital M1 plus capital M are behaving commonly plus M2. But you see, indirectly both the denominators are same only. So that is M1 plus capital M plus M2. And this negative sign is only showing that finally it is assumed to be moving, to be experiencing the recoil towards left. Okay, Ji? Right. Now you can compare. Both the answers are exactly same. Here this VR is giving you the magnitude because it's sign you have taken. Here I'm writing the vector. So vector is giving the same magnitude along with a negative sign. So this result must be same here. Must be same. Alright. But writing this is easy. One reason it is feeling based. Another reason you can do it in 1-2 steps. This is very long because it involves the relative velocity situation, relative velocity concept, as well as this concept that you are applying the conservation of momentum with respect to ground. I hope that's clear, and I hope you have liked this problem. Very important again, because man and boat is automatically a 2-particle system, but here 2 men on the boat is a 3-particle system, which can be further converted into 2-particle. All right, if you want, you can take the screenshot. All right. So we have discussed a lot of things. Now let's talk about few problems. Internal forces can change. Internal force can change linear momentum of the system as well as kinetic energy. Linear momentum but not the kinetic energy. Kinetic energy but not the linear momentum. Neither the linear momentum nor the kinetic energy. I hope everyone knows. Internal forces are capable of changing the kinetic energy, but they don't change the linear momentum. Linear momentum of a system can only be changed by external force acting on the system. Net external force acting on the system. Who said that? Newton said that. In which law he said that? Newton's second law. Newton's second law, which is also called as real law of motion. Real law of motion. Alright. Why it is called as a real law of motion, sir? Because Newton's first law and Newton's third law can be deduced, or they can be assumed to be a consequence of Newton's second law. Why that is so, how that is so, some other day we will be talking about. Okay. Next is a block A whose mass is 4m given is placed on the top of a wedge of base length 12 meters. So if you see, this base length is already 12 meters given to you. I'll write it like this. This base length is already 12 meter given to you, base. The mass here is, mass A is basically 4m, and block, the wedge mass is 20m. This is 4m mass, this is 20m mass. When the system is released from rest, find the distance moved by the block B till the block A reaches the ground. So they are asking you the displacement traveled by block B. Displacement traveled by B with respect to ground. So obviously where it is moving here, it will be moving in which direction? So when it is coming down, the block A, displacement of A in x direction is in this direction, cap I am writing unit vector, and displacement of B in x direction is in this direction. Cap means unit vector, direction. So I'm writing the displacement of B with respect to ground. That is, since it is in the forward direction, it should be positive, and always take the opposite mass. If you are writing the displacement of B, then you should be taking mass of A into the base length of base, है ना? Length of base, because that is the relative one, relative displacement by total mass of the system. That is the format, no? That is the format. So that will be equal to positive of the mass of A is 4m. The length of the base length is 12 meters by total mass of the system is 4m plus 20m. 4m plus 20m. So you see what you got, positive of denominator will have 20 plus 4, that is 24. Numerator will have 12 into 4, 48. 48 by 24, that is equal to 2 meters. 48 by 24, that is equal to 2 meters. I hope that's clear to you. Once again, I'm telling you, the displacement of B over the ground, that is always take the opposite mass. Here I'm writing like this again. You're writing for B. So the rule is always take opposite mass. That's what we have been talking about, right? In the entire session yesterday and today. These are the standard problems for you. And the base length is the relative displacement in X direction. You will be calling it as a relative displacement in X direction. Relative displacement in X. So opposite mass, relative displacement in X by total mass of the system. That's easy. Okay. Even if they ask for A, then also that could be written. Also, if they ask for A, suppose also the displacement traveled by A with respect to ground, that will be minus, because it is towards left, minus, and always take the opposite mass. If you want to take opposite mass, then you can write that opposite mass, that is mass of B. Mass of B is 20m into the relative displacement, that is 12 meters by total mass of the system, that is 20m plus 4m. Okay. So what you will be having here is denominator will have 24 mm get cancelled. 12 will cancel 24 at 2 times. 2 will cancel 20 at 10 times. So that is minus 10 meters. That is, this is plus 2 meters and this is minus 10 meters. Or else, in a better way, how you could have written it? You could have written it as displacement of A with respect to ground is basically displacement of A over the B plus displacement of, just making you practice this. I'm just making you familiar with it. Okay. Displacement of A over B plus displacement of B over the ground. Displacement of A over B is base length, is the length of base, and that too in the negative direction. Minus of length of base. Okay. Negative direction. Base length horizontal is traveled. Horizontally it has traveled base length in the negative. And the displacement of B over the ground is plus 2 meters. So minus of L of base is minus 12 meters. It is plus 2 meters, and hence the final answer is minus 10 meters. See, you are going to get the same result. All right. So there are always multiple methods, but my way, my shortcut thing is always, observation based or pattern based. Always take the opposite mass. That's going to be very useful for you. All right. Very nice. I can see many of you are answering. If you want, you can keep taking the screenshot also for a variety of problems. They will just make you feel, familiar with majority, with multiple questions, I would say. Okay. So now I'm also leaving few of the questions for you. 2-3 problems are there. Very soon we will discuss. And there are 1-2 more models jumping from a cart when we will be meeting very soon in the offline batches. Then we will be talking about it. But can I leave the remaining 3 problems for you? I want you to take a screenshot of this and then you can try it on your own. And the notes which will be attached in the description of the video by the end of the day will also contain these. So review everything and attempt these 3 problems. As of now, if you want to try in between, quickly take the screenshot. You have to try it. Take the screenshot of the next one. You will get these results within the notes also, and the approach also. Take the screenshot of this one. Answer is already given here. The remaining 2 you will find in between the notes. And this, if you try it on your own, the answer will be first one. For your convenience, I have taken that. All right. Chalo. That's all from my side. Hope everyone is comfortable with conservation of linear momentum, specifically emphasizing on two-particle system. All right. That's all from my side. All the best. Enjoy the rest of the lectures on the day and make sure to revise everything before you sleep tonight. Bye.